Our next example, I'm going to show you the inverse rotation matrix. That's really simple because we look at the first example for the 2D rotation, and this 3D only add this third row, does not change anything. And then you know the inverse is simpler. Change this negative to here. And you multiply, you're going to get the identical. So what is the inverse? Simpler, change this negative, that's to here. To find the inverse 2 by 2, you only need to do one round, use the shortcut I gave. 3 by 3, you need to learn how to use the Gauss-Jordan algorithm. To find that the major diagonal is a pivotal, then you do it column by column. And if more than that, of course, you use the tool. Maple, MATLAB, you calculate whatever you have. Next, we're going to look at the property of inverse matrix. If you have A have inverse, B have inverse, and then the A and the B could also have inverse, then A and the B inverse multiply inverse, you need to swap it to B inverse times A inverse. The other one is B A inverse equal A inverse times B inverse. When we talk about the GPS coordinate transformation, you're going to understand this very easily, why you need to swap it. The proof will give you the insight. If I want to multiply BA to the inverse, you're going to have to multiply A inverse B inverse. We know matrix is not commutative, but it's associative. That means you can group them differently. Equal B, A inverse, B inverse, and then A inverse equals I multiply anything is itself, and then B inverse, you get the I. That's why you need to swap. Well, once you get this property, let's look at the last example. I'm going to bring another coordinate system. This coordinate system is called the conventional inertial reference system. Last time we learned the Earth centered, the Earth fixed system. Means your coordinate is rotate with the Earth. But this time the inertial system, you don't rotate. That's it. And then your x coordinate always point towards the sun. And then this is inertial because you basically don't rotate, only revolute along the sun with a relatively constant velocity. That's called the inertia, no acceleration. When you have this rotated matrix with the Earth, you have the centripetal rotation. That's acceleration. That's not inertial. When you have the satellite coordinate, they usually give you by the conventional inertial reference system. Let's just call it inertial system. What's the difference? Well, the difference, of course, the Earth rotates 1 revolution per day. And then you can figure out how many seconds a day have. If you use a calculator or Google, you find one day have 86,400 seconds. And a day is 2 pi radian. That's 1 revolution. 1 revolution. And depends on your time, so you multiply the time. So after t seconds, the 2 coordinate rotated by this much radian. Well, in every day, at least one moment, the two coordinates will overlap, and then after this, they rotated apart. So how much apart? The angle is this, theta t. So to translate it, it's nothing more than you multiply this rotation matrix, A. To translate it back, you multiply the A inverse, which is B, a little difference. Again, the difference is this two, negative. So A is going to translate the inertial, I means inertial coordinate, to the Earth-centered coordinate. And the B as the inverse translated the Earth-centered coordinate to the inertial coordinate. Well, just think about, you sit down here, you're rotating. But the inertia means you should not rotate. So what do? You just multiply this matrix. Well, the next one, let's back to the DCM we started in the last moment of last lesson, is called the directional cosine matrix. The directional cosine matrix going to change the Earth-centered global matrix to the local matrix, the local coordinate. But inverse, just translate it backward. If you look at your notes, you're going to see this is the DCM. You start from the global matrix, you end up with the local matrix. So the inverse, you need to find the inverse of this A. You remember the first rotation, you rotated along the Z to the angle of the latitude to make the east direction overlap. The second rotation, you rotated along the east direction to make it the zenith coordinate overlap. That angle is the latitude, mu. So now you get the two inverse. Not only you need to multiply the inverse, in order to undo your old rotation, you need to undo it in the reverse order. Okay, now the inverse of A times B is going to be B inverse times A inverse by the property. So look, if I want to start from my local coordinate back at the global coordinate, what you do? You're going to get this A inverse first. Okay. This will be the A inverse first, and then B inverse here. So the original one, this is, where's the A? Oh, that's A, that's B. Oh, okay, the original is BA, then the inverse of BA is going to A inverse B inverse. And that is the B inverse, this is the A inverse. Of course, the order need to be reversed. Originally, you undo, you need to first to rotate along the east direction to the negative of the latitude. Then you're going to rotate along the Z to the negative latitude. Then you back into the global coordinate. Anyway, the bottom line is to reverse, all you need is multiply the reverse order product of the two inverse matrix. And it's very convenient. To do this calculation is a nanosecond for the computer, but we need to understand how to do it. So that's for today. See you next time. Thank you.